Right gang, what we're going to have a little look at today is some angular velocity and angular acceleration. Now, as you can see here, we've got an object that's spinning, it's the wheel of a skateboard. Now, we're going to tap into some previous knowledge in relation to linear velocity and linear acceleration, but we're going to have a little look at how it changes when we're working through calculations in relation to things that are rotating. Now, it's true that someone can only either move in a straight line or it can move at an angle, which would cause that rotation to take place. But before we do that, what we need to do is we need to be able to identify some of the key differences, particularly in relation to the symbols that we use when it comes to objects moving in a straight line and objects moving at an angle. And as you can see down the right hand section of, left hand section of the screen here, we've got the linear symbols, SUVATA, and then we've got the meanings here. But when we talk about something that's changing an angle, we use different symbols to represent that. The same Suvat formulas apply, which we'll look at in a second, but the symbols that we use to represent that information changes. So the symbol we use for angles, and you'll be relatively familiar with that one, is the Greek letter theta, and the units that we use for that is something called the radian. Now, if that's a stranger to you, bear with us, and we'll have a little look at what a radian looks like in a sec. Now, again, initial velocity is well letter U, but when we're talking about rotational motion or things changing at an angle, we use the Greek letter omega for that. Okay, now the units we use is radians per second. Alright, so much like linear, we've got meters per second, here we've got radians per second. Now, this can get a little bit confusing, but we use the same symbol for final velocity as we do for initial velocity when we're talking about angular movement. So what we have to do is we have to put a little subscript there. We'll put a 0 there for initial and a 1 there for final. And it might be that an object changes velocity again, so you might have a omega 2, omega 3, etc., so on and so forth. But the units is the same as they are in linear, are the same for initial as they are for final in relation to angular velocity. Next one, the Greek letter alpha for acceleration. And now we do use that symbol somewhere else in engineering, but we'll leave that alone for now. But much as, again, with a linear, we've got our distance, here it's meters, here it's radians, per second, okay, because linear acceleration is a change in velocity, angular acceleration is a change in velocity. Okay, last but not least here, we've got the T, which is representing time, and same units as we use for angular and linear. There's the seconds, and then for a minus acceleration or deceleration, minus omega, and that would be radians per second. Okay, so as you can see our Suvat formula here, we've got v squared equals u squared plus 2as. If we apply that to our rotational or angular motion, what that actually looks like is final velocity equals initial velocity squared plus 2 times the distance, 2 times the acceleration times the distance. So we've got final equals initial plus 2 times the acceleration times the distance. So it's the same formula, but we're using different symbols because there's different types of motion taking place. Okay, so we mentioned radians in the previous section. So this is actually what a radian looks like. So you can see it being generated here. It's actually simpler if you see this visual representation. So this angle here that you can see is 1 radian. Okay, 2 radians. So that angle is a radian. So when we talk about angular distance, we're talking about how many times that angle changes. Okay, so here we can see, and then when we look at that image, you can recognize that 1 revolution is equal to 360 degrees, which is equal to 2 pi. Right? Or if you think about it, a circumference of a circle is pi d. 2 pi. Okay, and that'll come in handy later when we start to move between revolutions per minute, radians per second. Okay, so you can pause the video at this point and have a little go at rewriting these SUVART formulas using the angular symbols. I'll let you do that yourself. Okay, so you can go back and forward as you wish. Okay, so as I mentioned earlier, we commonly have to change between RPM, revs per minute, into radians so that we can solve problems, and then we can go back again if we want to do revs per minute. So what we're going to do here is we're going to change 50 revolutions per minute to radians per second. Now this is something in one of our previous video, but we're using a different example. So we mentioned earlier that there is 2 pi radians in a complete 360 degrees circle. So what I'm going to do here, I'm going to take my 50 from my RPM and I'm going to multiply it by 2 pi, and I'm going to divide that by 60. And the reason I'm dividing it by 60 is because I'm taking it from minutes to seconds, and I'll pop that in the calculator and you can stick it in as well. So I'll do 50 and we'll get an answer of 5.23 radians per second. Okay, so if I get a question and it says I've got an object that's rotating at 50 RPM, I calculate acceleration or velocity or whatever it may be, I need to change that RPM into radians. So let's go the other way. So we've got 50 radians per second. Now we're going to flip this formula in and we're going to multiply it by 60 and we're going to divide it by 2 pi. And that will change it from radians per second into revolutions per minute. So I'm going to go there, so 50 times 60 divided by, and I'll get 477.5 RPM. Okay, so from revs per minute to radians, and then from radians to revs. Okay. Now, this is where the relationship between linear motion and angular motion starts to come into play. So we know this car is moving in a straight line, but to enable that to happen, that wheel has to have rotated. So what we've got here, we've got linear motion, but here we've got angular motion. Okay, that this linear velocity is equal to the angular velocity of the object it's spinning multiplied by the radius of the object. Okay, so I'll pop onto this next one and we can see we've got a rearranged version here. So we've got linear velocity equals angular velocity times radius. So we've got angular velocity equals linear velocity divided by the radius of the object that's spinning. So if it's a car tyre, yeah, it's the radius of that wheel. Okay, if it's a bike, it's the radius of the bike wheel. Well, you can see where these different values come from here. Okay, right, next bit. Now, to calculate or use angular velocity, some of the common questions that pop up in your exams that relate to rotational kinetic energy and linear kinetic energy, and multiplying them and finding the unknown values in relation to that. So we're going to have a little look at how we calculate rotational kinetic energy. But before we do that, we've got to first be able to get our head around this phrase, this moment of inertia. The moment of inertia is when inertia means that an object's resisting change in motion. Okay, so when we're talking about a moment of inertia, we're talking about resistance to change in rotational direction. All right. Now to calculate that, we need it's represented by the letter I. We need the radius of gyration, more of which in a sec. We need the mass of an object, when we need the radius of the object is spinning, and this squared is a constant. Okay, so these values may change, but the squared remains the same. Now, all of these formulas, this one in particular is given to you in any formula sheets you're going to be given prior to any assessment. So make sure you double check your formula sheets for the moment of inertia calculation if you need to do anything in relation to kinetic energy. Okay, so let's see how that actually impacts on our rotational kinetic energy formula. So we can see here, rotational kinetic energy is equal to half moment of inertia times angular velocity squared. Okay, now the more experience you get with these, the more you're going to be able to put that information there straight in to your calculation. But it may be that you do this bit separately, okay, and then you add it in, and it may be that you have to change linear into angular velocity. So again, the more experience you get with this, the more familiar you become. But just for reference, our rotational kinetic energy is half m v squared. So this half m, similar as we've got already, still got that half. The mass is in the moment of inertia, and then the v squared is our angular velocity squared. Now we might be given a problem where we have to mix and match between linear and rotational, but we'll cross that bridge when we come to it. There will be some more videos coming up where we look at actual worked examples using these formulas, so bear that in mind for future reference. Okay, now there was a phrase on that previous slide there, radius of gyration. Alright, now it's a pretty tricky one to get your noggin run, but we've got an example here. So we've got radius of gyration. You can see this object spinning. It spins around its centre, but as it's spinning, you can actually see as it's spinning, its mass is sort of moving in a strange motion. Now this is obviously a very sort of flexible bit of material. We don't tend to use flexible bits of material when we're getting objects to spin in engineering, but this is just to sort of demonstrate the radius of gyration. So what it actually is as this object's spinning, the mass of this object is focused at a specific distance away from its rotation axis. Okay, the radius of gyration is in meters, so, and we use the letter K to represent radius of gyration. Alright. Now again, you'll be given information to calculate radius of gyration, or you might actually be given the radius of gyration itself and then actually apply it. So always check your formula sheets, please, in relation to that. But what I'm going to do is I'm just going to jump onto the next slide, and you can see I've got several examples of objects that are spinning. Alright. We've got the same image as we had in the previous slide on the top left. We've got a car wheel here, looks as though it's from a Ferrari. We've got a bicycle wheel, and then we've got a cam. Now all of these things have got rotational kinetic energy. The car itself will have linear kinetic energy, but the wheel will have rotational kinetic energy. Now when we're calculating or trying to find the radius of gyration, these four objects are obviously they're all spinning, but the radius of gyration is going to be very different. Alright, so for a more sort of solid object, as it rotates, you'd expect the radius of gyration to be closer to the centre, whereas if you've got an object where the majority of mass is on the outside, yeah, you'd expect the radius of gyration to be further away from the centre. And then for this example here, you'd probably expect it to be somewhere in between. Alright, so again, check your formula sheets for radius of gyration, and then when you get given that value, it's always in meters. Okay, so don't get confused by any of the other units. It's always in meters. So when you go and apply that to your rotational kinetic energy formula, then make sure you're using those meter value. And again, you can check the previous videos in on the playlist for how to convert between units, etc. Okay. Alright, now in the next video what we're going to do is we're going to have a little look at actually applying those formulas. So using the linear and rotational kinetic energy and applying them to solving this problem. And we'll be using radius of gyration, calculate the angular velocity and all that jazz. So keep your eye out for those, and obviously if any of this stuff doesn't make any sense, go back, pause the video, make some notes, and then if you need any help, give me a shout and I'll try and explain it differently if that's what you need. Alright, but I'll just highlight that there. That one there is your rotational kinetic energy. So watch out for that in the upcoming videos. Once again, thanks for watching, and if in doubt, give me a shout. Bye bye.